Welcome to this tutorial video. In this video we'll be examining the first law of thermodynamics. You have in front of you a nice visual that we'll come back to. Effectively, thermodynamics investigates the energy changes within a system. A system might be a hot cup of coffee. A system might be air molecules trapped inside a balloon. Okay. In systems we're particularly interested in the internal energy. We give that the symbol U. Now the internal energy in a simple system can be changed by either adding or removing heat, given the symbol Q. And also we could do work on a system, or the work could be done by the system on the surroundings or environment. In each case we use the symbol W to represent the work done. We'll come back to this diagram shortly. Many of you will have seen or heard of the first law of thermodynamics, and in its essence it simply states that energy cannot be created nor destroyed. Okay? It is conserved. The system we'll be looking at is a basic syringe. Okay? We've all seen a syringe before. We have a plunger that can be moved freely in and out by an applied force. In this syringe we've got a fixed end that's sealed or capped, which means the gases, when you push the syringe in, or the plunger in rather, will be compressed and the dynamics will change. The four scenarios we wish to investigate are: number one, what happens to the gas molecule's internal energy when heat is added to the system? Number two, what happens to its internal energy when heat is removed from the system? And finally, number three and four, what happens to the internal energy of a gas trapped inside the syringe when work is done on the system and when work is done by the system? This notation of done on and done by the system is really important, and we'll look at that in more detail shortly. Let's examine the way in which energy, in particular kinetic energy, can change within a system. So first of all, you have what we call a vibrational kinetic energy, a mode of vibration. So here we have a polyatomic molecule, meaning many atoms, and it's possible in this structure for there to be bending or flexing within the molecule. It's also possible for stretching to occur. Okay, so if we add energy to the system, it may in fact undergo some vibrational kinetic energy of a bend or a stretch. It's also possible that there might be a rotational kinetic energy where the atom molecules might spin or rotate, in this case around the y-axis in a horizontal plane. You can also get a rotational motion in a vertical plane around the x-axis. And finally you have translational kinetic energy. Simple way to try and visualize this would be the breaking of a start of a pool game, okay, or billiards, where balls scatter everywhere. They have translational kinetic energy. We're not worried about how they spin, how they rotate. We're just looking at the fact they're moving or translating from one position to another. Now keeping in mind that it is in fact the average translational kinetic energy of a gas molecule that determines the sample's temperature. Some simple terminology. We use the symbol U for internal energy. It's a measure of energy, so it's measured in joules. We use the symbol Q for heat. Now heat is also a form of energy, so that's measured in joules. And we use the symbol capital W for work. Now work hasn't got the word energy in it, but it is also measured in joules. So the formula I have here is delta U equals Q plus W. It means the change in the internal energy will be equal to any heat that's added or removed, plus the sum of any work done on or by the system. So our first scenario, let's have a look. We have a fixed and sealed syringe. Fixed meaning that it's mounted and it can't move. Okay, and the plunger is fixed in its position, and we're going to heat up. We're going to add extra energy into this system. In this scenario, heat is being added into the system, so the heat Q is positive. It's increasing. As a result, there's an increase in the internal energy of the system. That should make sense. We're not doing any work. We're not moving this plunger at all. However, we're increasing the amount of heat into the system, and accordingly, our internal energy has increased. Using the PhET simulator, we can compare the effects of temperature upon a gas sample. So what we have here on the left and right is a sealed container with a thermometer, and we can add in gas molecules. One pump there, one pump there. We can see the gas molecules have translational kinetic energy. They're randomly moving around, they're colliding with the other gas molecules, they're filling the space, and they're striking the sides of the container, effectively exerting pressure. So this simulator allows us to measure the pressure and allows us to measure the temperature. There'll be some variation in the randomness of these two pressures. Okay, we'll use this one on the left as a control. Let's see what happens now if we add heat to the system. So if we can keep an eye on these particles, which I might add, you can see are randomly moving. Not all particles are moving as quickly as one another. Let's add heat and observe what happens. We notice our temperature has increased in the simulation, and we notice the pressure is building as well. But look at the particles on this right-hand simulator compared to the left-hand simulator. They've got much higher translational kinetic energy. Accordingly, their temperature is a lot higher. Far more collisions. There's more collisions per second. There's greater force being exerted on the perimeter of our container as well. Accordingly, our pressure is much higher. Let's now look at our second scenario. Again, we've got a fixed and sealed syringe, and this time we're cooling it. We're removing heat from our system. So Q is considered to be negative. It's reducing the amount of heat in the gas system. As a result, there's a decrease in the internal energy. Equation-wise, we can see that again, there's no work being done by the plunger. However, there is a reduction in the amount of heat energy, and accordingly, the internal energy is reduced as well. So as the temperature drops, and again, this is a simulator, it's an exaggeration, you can see that our temperature has dropped, which again is a measure of our average translational kinetic energy. The particles here are moving much slower than our control on the left-hand side. There's fewer collisions between particles. There's fewer collisions between the perimeter of the container, hence our pressure, which we know is a measure of force over area, newtons per meter squared, is being reduced. Also, you see the temperature is a lot lower because now our average translational kinetic energy is lower. Our third scenario is when we have a sealed syringe and it's allowed to be compressed as such. Okay, in this scenario, we can see that work is being done by applying a force on the syringe, forcing it to move a distance. And by definition, work is the product of force by displacement. Work is being done on the system. As such, the W is positive. We're adding joules into our system, and therefore there's an increase in internal energy. So again, our equation here, we're not adding any heat, but we have done work on the system, and as such, the internal energy increases. In this scenario, we're going to do work on the system. Okay, so we're going to apply a force through a distance or a displacement, and you can see the effect immediately. There's more collisions, particles are traveling faster compared to what we were on the left-hand side of our control. So our pressure has increased dramatically because there's more collisions occurring per cross-sectional area of the perimeter. And we know that the average translational kinetic energy, the movement of these particles, has increased because the temperature has increased substantially. So the more work done on the system, the greater the pressure and the greater the temperature, and the higher the internal energy. Finally, let's look at what happens when the system does work on the environment or its atmosphere. So build up of pressure, the syringe, or rather the plunger, is free to move, and it expands out, doing work on its surroundings. In this scenario, we can see that W is a negative. Work is being done upon the surroundings that's come from the internal energy. Accordingly, the internal energy will reduce. So we can see here, there's no heat being added, but work is being reduced. Okay, the amount of work done, there's no work being done on the system. It's being decreased. Therefore, the internal energy, okay, is dropping. Let's once again use our PhET simulator to investigate or try and simulate what happens when work is done by the system upon its surroundings or environment. Again, we've got our control on the left-hand side, 300 Kelvin and about 0.7 of an atmosphere in pressure. Now, for this particular simulator, I'm simply going to remove this boundary to the left. And in a way, it simulates what happens when pressure or work is done by the system to expand it. Such as, for example, gas inside a balloon that heats up and it has the freedom to expand. So if particles press sufficiently upon the boundary and it was allowed to expand, you would see that there is a slight reduction in temperature and indeed a slight reduction in atmospheric pressure. Okay? The particles are moving ever so slightly slower than what they were with the control. So the temperature has dropped because the average translational kinetic energy has dropped, and the force per cross-sectional area in terms of collisions on the side or the perimeter of this container has also been reduced as a result of the system expanding and doing work on the surroundings. Easy way to think about this: our internal energy will increase if we add heat. It will decrease if the system gives off heat. Our internal energy will increase when work is done on the system, such as compressing a gas, okay? And our internal energy will be reduced when the work is done by the system, such as expanding a gas and allowing it to release and do work on the surroundings or the environment.